Welcome to this first lecture. So, as Shamik just said, it's a good habit to be on time, but I have to give you motivation to be on time. So, and the motivation is that what I'm going to teach you is actually, it's a very important subject in quantum many-body physics, but it's also a very obscure subject that it's very hard to learn from books. Simply because there are books that are very, new books are written reasonably well pedagogically, but old books were written mainly close in the factory of books close to the Landau Institute, and they're not very clear, let's put it this way. They're not very clear to the extent that when I learned myself the Keldysh formalism, and that was 25 years ago, it was something that you traded with people. You went to other students and you told them, I'll give you 2 Matsubaras, you give me 1 Keldysh. So you kind of tried to get it from people because it was very hard to understand it deeply from books. And the reason it's hard to understand, well, first of all, what it is. So the Keldysh formalism is essentially the way to generalize all the formalism you love and use all the time to deal with many-body systems in equilibrium, so field theories, essentially. So the time-ordered green functions you use for zero-temperature field theory, Matsubara formalism, imaginary time formalism, etc., to generalize this to deal with non-equilibrium quantum systems. When it was invented? Well, it was invented in the last century. It's already, quite, it has already quite some time. It's pretty old. It was invented by people when they started applying the ideas of many-body physics to non-equilibrium problems, in particular in the context of transport. So the first systems to which the Keldysh technique was applied was transport problems in semiconductors, superconductors, Fermi liquids, even superfluids or bosonic systems, whatever you want and like, but essentially condensed matter, quantum condensed matter physics. And over the years, it was understood that it has deep connections with classical statistical mechanics, in particular the Doi-Peliti formalism and various other connections that I will not explore in these lectures because I'm going to be very simple and pedagogical. So the goal of my lectures, so these are lectures that I've given for probably 20 years in Trieste to students there. And the goal has been always the same. So what I want to try to do is, in 5 lectures, to make you capable to do calculations using the Keldysh technique. So I don't care about telling you the, principia of whatever. It's not important to me. I want you to learn the formalism and to be able to set up, write the Hamiltonian, choose your small parameter, do your perturbation theory, and do whatever you want with it. And in order to do so, what I will do is I teach you the formalism with a hands-on approach. So I'm not going to give you the general principles and then eventually after 3 lectures give you a couple of applications. No, what I'm going to do is I'm going to start with concrete problems and show you how the solution of those concrete problems will lead to certain steps in the formalism and eventually make you understand why this is such, why you need to use triggering functions, why you need to do the analytic continuation, why you need to do this and that in order to solve a concrete problem. So where will I take the problems? I'll take the problems from what I think is the simplest realm in which you can apply the Keldysh quantum version of this non-equilibrium formalism, which are problems in transport through nanostructures. So quantum dots, quantum wires, all of this stuff. At the end, we will have also something about dephasing and dissipation. Why? Because these systems are simple. I understand very well the physics of the systems because it's what I grew up with doing mesoscopic physics at the Weizmann Institute, and so I can make a connection between the formalism and the physics in a pretty direct way, and make you understand the details of the formalism, what a single green function or a single operation on a green function means by looking at physical details. So nothing is going to be abstract here. So books, as I told you, it's a subject in which you can find everything, but everything is hardly understandable. I mean, unless you know how to use the formalism already. So, of course, there is a chapter in Landau-Lifshitz, LL. In the last book that was not written by Landau, Physical Kinetics, there is a chapter on the Keldysh technique. Try to read it after you listen to my lectures, and you can tell who is better, whether Lifshitz or Silva, okay? So this is Lifshitz. Then there are a few old reviews by Rammer, Smith, nice, but very much focused on transport through, for example, superconductors. There is a nice book that I like a lot, very pedagogical. Part of what I'm going to tell you is inspired by what is written in this book by Yao. It has a strange name. It's called Physical Kinetics of the Semiconductors and Superconductors. It's about the Keldysh technique. I don't know why he called it. He gave it this complicated name. And then there is a wonderful book by Alex Kamenev. It's called Non-Equilibrium Physics of Quantum Systems, or something of the like. It's a great book. It's probably the best book on the Keldysh technique available on the market. However, it uses path integrals from the beginning. No second quantization, no standard operator formalism. Therefore, my suggestion is you listen to my lectures, you redo the calculations in my lectures, then you buy this book and you read it. And then you will know Keldysh perfectly well. And in this book, there are all connections between the Keldysh technique and the classical non-equilibrium theories like Doi-Peliti and company. So if you're also if you're interested in classical subjects, it's not a waste of time what I'm going to teach you. Okay, so that's it, I think. Well, there are other stuff. If you want to suffer, you can read the book by Kapnin. It's called The Non-Equilibrium Superconductivity, and enjoy yourself. But this is, really, it's what I call it's like, when you go and see paintings or you don't understand anything. It's like listening to German opera, right? You like the music, you don't understand the words. So for me, not for Michael. All right, so let's start now with, I have to learn how to use this. So as I promised, I'm going to work with a hands-on approach. So the first thing I will do is write down what are the type of Hamiltonians we will be solving, dealing with, etc., and what are the type of non-equilibrium problems I'll be discussing. So one standard problem we'll be dealing with a lot is the following. You have two electronic leads, two pieces of metal or whatever. Typically they are made in a two-dimensional electron gas in reality. But imagine two Fermi seas, right? The left Fermi sea and the right Fermi sea with standard Fermi-Dirac statistics. And now what you do is you put in the middle something and you connect these two Fermi seas and you make a current flow. So what can be this something? For example, you can put a single resonant level with an energy, I don't know, epsilon naught. Or you can put a single resonant level that is coupled to phonons. Or you can put a single resonant level in which, when electrons are sitting in the resonant level, they're interacting. So you can, if you put two of them, you have to pay some energy. So all of this, you write it this way. You say, my Hamiltonian is, I assume that all of you are familiar with second quantization formalism. How many of you took a course on field theory? Raise your hand. Oh, fantastic. Almost everybody. Okay. For those who didn't take a course on field theory, the book in which you can learn part of what I give as, for granted is, is Mahan. It's a big, thick book you can use to kill a person. And so it's not my favorite book on many-body physics, but it's very pedagogical. And in the first 2 chapters, you essentially learn the basics of, standard perturbation theory in the second quantization formalism. So if you're not familiar with certain things I'll say, just go to this book and read the first 2 chapters. You can do it tonight. I'm sure that you can find a PDF. I shouldn't say this. Okay, so we have the two electronic leads. And so we have their energy, epsilon k, assume a certain dispersion, is not important what it is. And then I have some fermionic operators with standard anti-commutation relations. And sigma is a spin. I'll put it just for completeness, but it's not going to play a major role in what I'm going to say. Then I have this guy here, the resonant level. So it's just one level, one level, with some, these are fermionic operators again, that represent the electrons when they are sitting in this particular level. And then I said, I want to close the circuit, so I want to make electrons jump in and out. And therefore, I'll put what is called an hybridization term, which describes the tunneling of electrons between the 2 fermionic leads. And the resonant level. Now, you can put one resonant level, you can put 2, you can put many, you can put a continuum, you can put whatever you want in the middle. You should think about this middle as the picture you draw always when you do high energy physics, right? High energy physics, you use field theory to compute scattering cross sections, roughly speaking. And they always draw the picture that here is the scattering region, you have some incoming particles, you have some outgoing particles, and here happens who knows what, but eventually something free comes out and you want to figure out what is the relation between what goes in and what goes out. Well, here is essentially the same story. So here we have something. It's a resonant level, it's an interacting resonant level, it's a bunch of levels, whatever. But here we have 2 fermionic leads that are free. And what we are interested in is the relation between what goes in and what goes out. So in practice, what we want to know is what is the current that is flowing, because that's what you measure, right? You don't measure cross-sections in condensed matter physics. You can measure the current, the noise of the current, and all these kind of things. So in practice, one way to represent this in the Hamiltonian is to say, well, maybe here I will have some interaction term that will involve the operators in the resonant level, will involve perhaps some other operators, maybe some bosons, something else, who knows, but will never involve operators in the two leads. Why? Because if I put operators in the two leads in the scattering, in the interaction term, then it's as if in a scattering problem, I'm saying, oh, well, this is not as free. These are not free particles that move, and all interactions happens here. Interaction happens also here. Well, then, try to formulate the scattering problem if you're able to with this kind of setting. Now, you can tell me, well, this is not accurate. Electrons are interacting particles. What the hell are you talking about? So there is some interaction right here. Well, the logic that stays behind this reasoning is the Fermi liquid theory that tells you that essentially all transport, we will see it better later on, but transport problems, you know it from Drude theory. You all know Drude theory, right? So when you do Drude theory, you don't care about what is happening to electrons that are sitting 2 million electron volts below the Fermi energy, because they don't participate to transport. The only important electrons are the ones that are sitting close to the Fermi energy, because those are the ones that move around, scatter, do stuff. And then current is going to be determined by those electrons. Well, it turns out that if you put interactions, electrons close to the Landau taught us that electrons close to the Fermi energy are essentially free particles with some renormalized velocity and something else. So to lowest order in the level of difficulty, therefore, I can describe this transport problem thinking about the two leads as free electron leads, okay? And that's it. So I'm not only theoretically, it's not only theoretical advantageous for me, but it's also meaningful physically. And actually, you can use what I'm going to tell you to make predictions about transport problems in mesoscopic systems. Now, you can ask me a question, very brief comment. You could ask me, well, is this story any relevant for something physical that is being measured in experiments in real systems? Yes, it is. It has been for 30 years. It turns out that you can take what are known as semiconductor heterostructures, which are essentially wafers like the ones you eat in the morning, perhaps, in Switzerland, certainly. And so these are made of two different materials. The best one are made of gallium arsenide, aluminum gallium arsenide. And because of some impurities here, donor impurities, what happens is that you form a two-dimensional electron gas at the interface of these two guys. And this is where the quantum Hall effect, the fractional quantum Hall effect, was originally measured. Well, the quantum Hall effect was measured in silicon MOSFETs, but it's roughly the same story. So now, if you take this, so imagine that here you have your favorite two-dimensional electron gas, so electrons swimming in two dimensions. If you now put some gating here, you evaporate some aluminum, typically, stuff on top of your heterostructure, and then you put a voltage on it, what happens is that you deplete the electron gas below it, and you can draw on the electron gas all the structure you want and you like. For example, you can draw something like this. And this is essentially that. Because this constriction here creates a tunneling barrier. Here you have a constrained region in which energy levels are quantized, and here you have the second lead. So left and right. So essentially, this is, before Michael was talking about quantum simulators. The first quantum simulators that I grew up with were actually the quantum, nanostructures or whatever, in which we could recreate transport problems like quantum dots or quantum wires using real stuff. Well, now the story that Michael told us is actually much more interesting in a sense, because in those systems you're dealing with closed systems, thermally isolated, at least for some time. These ones are not. Here you have a lot of dissipation, dephasing, all sorts of complicated issues. But, let's neglect this and move on. Right. So, now, interaction. What kind of interaction could we be dealing with? Well, so the most famous interaction term is this one. So it does not involve anything beyond the operators that I already wrote in the Hamiltonian. If you take that guy with this interaction term, it has a name. It is called Anderson model. Yes. Yeah, I usually tell students that I work in units in which h bar is equal to c is equal to pi is equal to 1 is equal to 2 is equal to minus 1. And so it's equal also to dagger. But then I tell them that in the exam it's not valid to use these units. Okay. Yeah. B can be, I just wrote it to say that you might add some interaction with some external particles. Maybe I'll write an example later on. So this is the Anderson model. What is the physics of this model? If you put 2 electrons in the quantum, in your resonant level, then you have to pay some energy, some charging energy, because of electrostatic interaction. Now, this is a very important model because it's essentially, it has the same physics as the Conde effect that maybe some of you heard is one of the first most important non-perturbative blah, blah, blah models in condensed matter physics, but it's a complicated model to solve. It has very non-trivial physics that I cannot explain today because it's out of the scope of these lectures. But if you're interested, Mahan has a chapter on it. Now, another model, just to answer the question of that Shamik asked, could be the following. You just say, okay, well, let me add some sum over sigma, d dagger sigma, d sigma, and then sum over q, lambda q, b dagger q, plus b of minus q. So this is essentially a rough version of electron-phonon interaction. So this would be the displacement of the phonons, and the physics you're trying to describe here is that an electron comes in the quantum dot, displaces some lattice or does something to some other degrees of freedom and starts emitting and absorbing phonons from inside. So it's a rough way to describe dissipation as happening inside the resonant level. Right. So now this said, what do we want to compute? When we have this type of problems, what is interesting and important to compute? Well, there are various things. One thing, for example, the simplest that we could try to compute is how many electrons are sitting on average as a function of time inside our quantum dot. Why not? So using the standard notation, O of t, and from now on, this thing here is going to disappear. So they are all operators. E to the I h t, or e to the minus I h t. Then, well, the occupation of my quantum dot, n of t, is going to be equal to sum over sigma n sigma of t, which is, of course, equal to sum over sigma, d dagger sigma of t d sigma of t, right? So this is one thing, a natural thing to compute. How many electrons are sitting there on average? Another thing you can compute that is perhaps more important is what is the current that flows through the quantum dot. So the current, you define it as the current that flows out of lead alpha, where alpha is equal to left or right, is equal to minus E. E is the electron charge. It's going to disappear soon and become equal to pi minus 1 and everything else. dn alpha dt. And this is equal to minus E times I times sum over k and alpha, v alpha, and then d dagger k alpha c, sorry, d dagger, no, I made a mistake, k sigma, d dagger sigma, c k alpha sigma, t t minus complex conjugate. Okay? So this is the current that flows out of lead alpha. Now, of course, the current that flows out of lead alpha is equal to alpha, let's say alpha is left. That current that flows out of the left is equal to minus that current that flows inside in the right lead, provided that there is no charge accumulation within the resonant level. That might happen in the transient, but not in the stationary state eventually. Otherwise, the energy would grow, 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 grow forever. And then, given this, you can compute other interesting stuff. For example, one thing that is very important is the noise, is the spectrum of the noise of charge, which is integral dt e to the I omega t, and then, well, it depends how you define it. I take the antisymmetric correlator, so the symmetrized noise, and then that's, no, wait a second, t naught plus t e alpha t naught. Right. Wait a second. Okay, here I have it with a minus sign. Is it correct? This has to be real. So minus the complex conjugate is the imaginary part, and then there is an I here killing it. So everything is fine. Right. So now you look at this and you say, haha, well, I have to compute the averages of operators. That's what I have to do, right? So that's your goal. And now you try to understand how to do that. Now, if this would be an equilibrium problem, then it's clear that you would understand all these averages, these ones, as meaning trace with respect to the equilibrium density matrix of something, right? And the equilibrium density matrix is e to the minus beta h minus eventually mu n, if you want to put a chemical potential, divided by trace of e to the minus beta h minus mu n. Okay? So everything works. But in real life, when you try to solve this problem out of equilibrium, I mean, of course it's interesting. Let me just state one thing. It is interesting to compute these quantities in equilibrium. It is very interesting. For example, well, the average, we will compute in a second at the end of this lecture the average occupation. You will see what is the result. Not very exciting. The average current, of course, is 0, right? Because, well, there is no current flowing. There is nothing that breaks symmetry. What about the noise of the current? Well, in equilibrium, even if the average current is 0, you still have charge fluctuations, right? And those are determined by essentially by the temperature. So this is called, wait a second, it's called Johnson-Nyquist noise in the literature. And it's proportional to the temperature or to the temperature squared. I don't remember, perhaps to the temperature. But it's proportional to the temperature to some power. So it is interesting to compute it, right? But the thing is, we're not interested in these lectures to deal with equilibrium systems. We're interested in dealing with non-equilibrium systems. So what is the simplest way to take this system out of equilibrium? Of course, I mean, I can take all the parameters and make them time-dependent. That's one way. But there is also another way that describes, for example, what is going on there or what is going on in that circuit or whatever, which is when I click the, how's it called, the switch there, what happens is that I close a circuit. And I close a circuit in which I have two parts that have a different potential, and I just connect them, and current starts flowing, right? So here I can do the same by saying, okay, at time t equals 0, I have these two guys that have different chemical potentials. So, and they live there in equilibrium. They don't do anything. And then at time t equals 0, I connect them through this scattering region, and I see what happens in the stationary state. And so this is my standard problem I will want to solve, okay? So now I will start telling you, first of all, what will fail in the standard way of constructing a perturbation theory or a field theory if you try to solve a problem of this type using the formalism you already know. I will tell you where it fails precisely. I just pinpoint, look, here, and here, it explodes. And then I will show you what is the solution in equilibrium. And then next time, we're going to cure those little pieces in which the formalism doesn't work. We're going to modify it. This is what Keldysh did in such a way as to make it work for the general case out of equilibrium. So that's the plan. Right. So, yes? What is? Alpha. Alpha is left or right. Is left or right lead. So here is alpha equal left, alpha equal right. Yeah, these are the fermionic creation and annihilation operators for this guy, for this resonant level here, for an electron in this resonant level. Let me go back to the Hamiltonian. It's like, see? See the Hamiltonian. Look at the Hamiltonian. D is this. C are the creation and annihilation operators of the two leads, of the two sides. Okay? Clear?
There are different C's for left and right?
Yes. So there is CK left and CK right. Oh, but perhaps you're complaining that here I called it. Oh, you're right. Well, now you immediately understood that with me you have to interpret what I write depending on how high it is. So, yeah, so you understand now? Is it clearer? And alpha is equal to left or right. Okay, I'll try to be more precise. Okay, but not too precise. Yeah, so I told you that I computed the current that flows out of lead alpha, let's say out of lead left. But it doesn't really matter, because if you're in a stationary state, what goes in is what goes out. So the current that goes in from one lead is minus the current that goes out from the other. So
You just calculate V and
yeah, I just calculate 1. Other questions? Is everything clear up to now? It's going to get more complicated, but not now, not today. All right, so now let us see where things go wrong, okay? So I can use this, right? So the story is the following. Typically, and here I'm jumping forward, when you want to compute averages of operators, one of the greatest achievements of physicists who came well before us was to understand that actually to do a perturbation theory, imagine you want to compute this in a perturbation theory, I don't know, what is the small parameter? Let's say in V. I use this as small parameter, why not? It could be a small parameter, the tunneling. And I want to compute this perturbatively in V. Well, people realize that if I do perturbation theory directly for this operator, it's going to be a disaster, a major disaster. It's going to be extremely complicated. If you read the original papers by Schwinger, who was trying to solve problems of this type with operators for high energy physics back when this institute was built, formulas are enormous, right? I mean, you really, it's very hard to follow. But then people realize that there is an object that is not directly a physical object, that has a much better behaved perturbation theory, and that is known as the green function. For zero temperature, the green function is defined as the time-ordered product of d sigma t d dagger sigma t prime, right? So what time ordering means, let me remind you, is that you put on the right who comes first, right? D dagger sigma t prime equal to theta t minus t prime d sigma t d sigma t prime minus the minus sign comes because I'm dealing with fermionic operators, and then theta t prime minus t d dagger sigma t prime d sigma t. Right, so the story is typically what you do is you take a discrete function, and you know that if you're dealing with this green function, thanks to a theorem that was proven by a guy, so the Wick theorem, and by the way, Wick was Italian, just to make sure that you know this. So thanks to the Wick theorem, then you can do a very nice perturbation theory for these objects. Because what happens is the following. You take this green function. Let me remind you what are the steps. It takes this green function, and the first thing you do is you go from the Heisenberg representation of the time evolution here to the interaction representation. So what you do is you write this as time ordering of e to the I, H, well, do I need to do this? Yeah, well, perhaps. I'll do it just for the first, otherwise it's a nightmare. And the same for the other, for the dagger, okay? you go to the interaction representation. So the interaction representation is the representation in which the operators are evolving with the bare Hamiltonian. For example, if here I was doing perturbation theory in V, the bare Hamiltonian is the one of the two leads. Well, I don't want to have an interaction. Let's say it's a non-interacting system. So H interaction is equal to 0. I have the two leads and the resonant level. And I do perturbation theory in this. If I want to do perturbation theory in H interaction, I take the quadratic Hamiltonian as H naught, and I treat H interaction as the perturbation. That's how it works, okay? So it's always up to you to decide who is H naught and who is H interaction. The only important thing is that H naught has to be quadratic. Otherwise, you're expanding around a minimum that is very complicated, and you don't know how to deal with it. Right, so now we go to the interaction representation, and a good way so the operators are evolving with H naught. The states are evolving with the time-ordered exponential. So this thing here, e to the minus I, e to the I H naught t, e to the minus I H t, is the time-ordered exponential of e to the minus I integral 0 t dt prime of, let's say that I wrote my H as H naught plus V. This is going to be e to the I H naught t prime V e to the minus I H naught t prime. Okay? Chapter 1 of Mahan. So if you're kind of shaky on this. Right, so I pass to the interaction representation. After I pass to the interaction representation, this guy here, typically I call it U of t, or whatever you want. It can have many names. But you give it a name because now it becomes easy to write your green function, G sigma tt prime, as minus I t U dagger t d sigma t U of t U dagger t prime d dagger sigma t prime U of t prime. Okay? That's what it is. Now you introduce, and so the name, it's actually, it can be made precise, but originally all of this comes from high energy physics. You introduce the S matrices, S of t prime. So this is defined as U of t, U dagger of t prime, and is nothing but, if you write it as the time order exponential minus I 0 t prime t dt double prime of v t double prime. So this is the S matrix. And the reason you introduce this S matrix is that now you can write your green function in a way that is actually physically interesting. I will explain in a second. So first of all, we are doing zero temperature perturbation theory. So here we have the ground state, and then T S T S 0 T d sigma T S T T prime d dagger sigma T prime, and then S T prime 0 psi naught. Okay, so look at the structure that comes out of this stupid manipulation. So I introduced this S matrix for my interaction representation, and I just look at the time labels. And you see that here the time is going from 0 to t prime, from t prime to t, from t to 0. So it's doing something like this: 0 to t prime to t, and then back to 0. That's the structure that comes in the the algebra, nothing else. I'm just giving it a visual representation and nothing else. So it has no other meaning than a visual representation. And now I look at this and say, well, now I don't know what to do with this practically. I don't know how to deal with this, this green function. But then came two guys, Mr. Gelman and Mr. Lowe. And they, you know, their intuition was clearly the key point to develop the whole field theoretical formalism. And I'm sure that Gelman was aware of it. And I was told by students that at some point he was going to a lecture, and outside there was a thunderstorm like today here. And then he waited until he realized that the thunder was striking, and then he entered the room, right? I wanted to do the same today, but it didn't work. Anyway, so, but this story that I'm going to tell you is really a major achievement. Why? Because they realized, they said, well, here you cannot do anything. Why you cannot do anything with this formula here? Because psi naught here, when you take the average, is the interacting ground state of your theory. And you don't know it. So you have to do perturbation theory. So how is the interacting ground state of the theory connected to the non-interacting ground state of the theory? And Gelman and Lowe realized that this is done in the following way. The interacting ground state is equal to the S matrix operating between minus infinity and 0, acting on the non-interacting ground state. I'll put an epsilon here, and I'll tell you what it means in a second. So you take your time evolution from minus infinity acting on the non-interacting ground state, and you take it to time t equals 0, and you will get the interacting ground state. This epsilon means that you're adding a small regularization to your integral in which you're adiabatically switching on the interactions with an adiabatic parameter epsilon that eventually will send to 0, right? But the meaning is that slowly, you're turning on your interaction, and you're thinking that I'm starting from the non-interacting ground state, eventually will end up in the interacting ground state. Now, this is pretty meaningful. Think about the Fermi liquid. Fermi liquid, yeah, there is a paper by Stefan Kerain and I think what's his name, Marcus Heil did this calculation properly a few years ago, but you start from minus infinity with a non-interacting ground state, then you turn it on very, very slowly, and eventually you will end up with the Fermi liquid, right? So here the idea is the same. So start from minus infinity, goes to plus infinity. Now,
isn't this the content of the adiabatic theorem?
Well, yeah, yes, it is. However, strictly speaking here, there is some, so you're applying it to, you know, at the end of the day, you're applying, you know, the reason it's a conjecture is that strictly speaking, you're applying it to systems in the thermodynamic limit. When we do these calculations, we never think about having to deal with finite-sized systems, with finite gaps, because, you know, the adiabatic theorem will never work for a system that does not have a gap, right, for a continuous system. Here, when I write my Fermi gas, I'm not thinking about having a finite-sized system. I think about a, you know, thermodynamic limit from the beginning. So that's why this is called the Gelman-Lowe conjecture and not the adiabatic theorem. The idea is that, but it's actually much more subtle, okay? Now, if I now take this, let's call it number 1. There is a number 2 that is important, that apply it to the formula there, what I get is that my G naught TT prime is equal to minus I phi naught time ordering S of minus infinity 0 d, minus infinity t dt S of tt prime d dagger t prime, and then s t prime minus infinity. Yeah, I managed to use the whole black part, phi naught. Okay?
How is it guaranteed that Scheiser is the ground state of the...
It is not. It's a conjecture, right? So it's a kind of, in Latin you say ipse dixit. He said so, and we just trust him. So it's a conjecture. So you can say, I don't know if it is proven. I know only this calculation in which it was done carefully, and it was shown that for a Fermi gas it works. So typically when it doesn't, it means that perturbation theory doesn't work, right? You cannot construct a perturbation theory. For example, if you try to do this for the Anderson model at 0 temperature, when the resonant level is well below the Fermi area, you have an effect which is called the Konde effect, which is non-perturbative in U, and therefore eventually you will not catch it by doing this construction. So in that sense it doesn't work, right? But it's a subtle thing. I mean, it's a sort of total. When perturbation theory works, then the Gelman law conjecture works, in a sense. I don't know how to say anything more meaningful than this. But you see what comes out of this. What comes out is that now I solved my problem of the ground state there. I have the non-interacting ground state. And the only price I paid is that instead of starting from 0, I go from minus infinity to time t prime, then to time t, and then go back to minus infinity. Right? So this is the structure. You see? But then you look at this and you say, aha, well, but look, I don't know how to do, what is this? Right? I know how to do integrals over real time axis. I mean, time is running from minus infinity to plus infinity. Not this strange thing here. So eventually we want to take this and visually stretch it to the other side. And then Gelman and Low realized how to do that. They said, well, look, if you have an equilibrium system, then if I take, where is it? If I take phi naught and act on it with the S matrix, from minus infinity to 0, I turn on adiabatically the interaction, and then I turn it off adiabatically, so on and off. I go back to the same ground state I started with, up to a phase factor. So that's the second part of the Gelman law conjecture. Now, if I use the second part of the Gelman law conjecture, then I can take this and say, well, look, you don't need to worry about strange contours over time, because now you can apply the second part, put the phase factor here, and what you will get is that this is equal to minus I phi naught. Then you will have S matrix plus infinity T d dagger T S T T prime D T prime, and then S T prime minus infinity. And the price you have to pay is that you have that phase factor, that one, and that phase factor is nothing but phi naught S of plus infinity minus infinity phi naught. And now you're done, because now this collectively you can write it as S plus infinity minus infinity because of the time ordering, because everything is falling inside the time ordering sign, d dagger T sigma T prime. And you see that it has the structure that you all love. Now you can take your S matrix, that is a time-ordered exponential, start expanding it in power series, then start taking contraction using our friend Wick, Vic, and you build your diagrams one by one. So all the machinery starts from here. And this phase factor that we got by stretching that contour and making it become the real axis is actually very important in the construction of perturbation theory. Because you see, I'm sure that all of you have seen, how many have seen Feynman diagrams? Almost everybody, almost everybody. So you all know that when you expand if I would expand the S matrix here and start taking contractions, I would get all sorts of contractions. For example, I would get the bare green function, then I would get the bare green function with, I don't know if I have electron-electron interaction with things of this type. But then I could get also this kind of objects. You know, the bare green functions with glasses. And do I have to include this? No, I don't. I can forget about it. Why? Because of this normalization. Because in this normalization is telling me that all these diagrams, the glasses, and then, I don't know, I can, this one, and then everything that is a disconnected diagram is eventually normalized. All of the sum of all these guys is eventually normalized by what stands in the denominator, right? And then I can forget about them. So it's a major simplification. You can expand your green function and forget about the disconnected diagrams. The only ones that will contribute are the connected ones. Why? Because of this. Why? Because of the Gelman law conjecture. Clear? I hope it's clear to everybody. Yes? Yes. Yeah. So what I did was, okay, maybe I went a bit too fast. What I did is I put in here, wait a second. I multiplied and divided by e to the IL. And therefore, so here I have e to the IL, and then I divide by e to the IL. You see that e to the IL times this is equal to s plus infinity minus infinity over this. And then I multiply by this. I goes from t to minus infinity and then to minus infinity from plus infinity, and that's what I get. Okay, clear? Okay, other questions? Right, so now it's my turn to ask questions, right? So what goes wrong? What could go wrong when you go really out of equilibrium in the Gelman law conjecture? This one? The bottom one? So can you make your argument a bit more precise? So when you start from the ground state, you go to the ground, and then eventually, at long times, you will go to something more messy. Right. So I typically make the example to students who are not as clever as you, I have to say, because I always need a few a few minutes before students answering. Yeah. So I always make the example. Suppose that we take this room, right? And I turn off the lights, so that's my ground state, non-interacting. Then I turn the lights on. It's the ground state, the interacting ground state. Not interacting ground state, is the interacting non-equilibrium state, right? And then I turn the lights off, okay? So do I end up in the same state I started with? I can check. I can also check, but it's a very subtle how to check it. But is it clear the question? You go back home tonight, you're sitting in your room, it's dark, you turn on the lights, and then you go to sleep and you turn them off. Is the same state you started with when you entered the room. Imagine doing it in a quantum world, right? Is it the same state? Let's say the answer is no, but why no? Because when you turn on the lights, you emit photons. And those photons are gone. I mean, you know, it's true that when you turn off the lights, you don't see them again fluctuating around. That's because they've been absorbed by you, or by the furniture, or by something, right? So eventually, you would be able to detect that they were emitted by a slight increase in temperature or something else. But the state of the system at plus infinity is not the state of the system at minus infinity. And that's a characteristic of non-equilibrium systems. Otherwise, there is no breaking of symmetry of time translation and invariance, right? So it's because of dissipation, roughly speaking. So you see that if I am out of equilibrium, truly out of equilibrium, this part of the Gell-Mann law conjecture is gone. You cannot use it. And therefore, you immediately see that this structure here, in which I could deal with everything on the real time axis, is gone. It's not there anymore. I'm sorry, you have to deal with this. Time is running in this strange way in the quantum world, out of equilibrium world. By the way, this has a name. It's called the Keldysh contour. We'll see how to use it later on. But now you understand where it comes from. Okay, so there is another thing that doesn't work out of equilibrium. So this is one. So bottom line of this first story is, if I'm out of equilibrium, I cannot do perturbation theory in the usual way using the real-time axis. The system forces me to have reference only about the initial state and not about the final state. And this is natural. When you solve differential equations, typically, you give an initial condition when you solve for the dynamics. When you solve some kinetic equation, you give an initial condition. You refer only to the initial time. You don't know what is going on at the end, right? So same story here. We refer only to what is going on at the beginning, but not at the end of our evolution. That we can do only in thermal equilibrium or at zero temperature. Now, the second problem with non-equilibrium Green functions. So with Green functions. Yeah, this I had done at zero temperature just for simplicity because I didn't want to introduce Matsubara, the imaginary time and do complicated things. But, the structure is essentially, well, for Matsubara it's actually even more. I mean, for Matsubara it simply doesn't work. Matsubara requires you to make averages with respect to the equilibrium Green function, and all the time evolution is actually a sort of fake time evolution. So here, because it comes only through the interaction representation. So
just to be sure, the number 2 point is not going to work even at zero temperature.
If you're out of equilibrium, even at zero temperature, it's not going to work. It has to go with equilibrium versus non-equilibrium. Actually, when you're out of equilibrium, even thinking about the distinction between zero temperature and finite temperature is very fishy in a sense, right? Because immediately you start occupying your states in a non-equilibrium fashion, right? So your distributions are not just just Fermi-Dirac distributions at zero temperature, right? So second thing, I told you that, so we did our perturbation theory with the retarded with the time-ordered Green function. But I'm sure that all of you know, because you're all very good, that there are plenty of Green functions. They're not only time-ordered Green functions. So for example, when you compute scattering cross-sections, the most convenient thing to do is to use retarded Green functions. because they describe stuff as you know, in a not casual, but okay, I'll write it. I don't know how to pronounce it. I mess up with the causal way. Right. So, and these are the green functions with the anti-commutators. And with the theta function here. So it goes only forward in time. And then there is the advanced green function, which is I theta t prime minus t. So this goes backward in time. And then I have the same anti-commutator. And then I can introduce other green functions. So what I call statistical green functions. So when you want to use, for example, the time-ordered green function to compute, I don't know, the average occupation, you need to do some trickery, right? Because you need to say, well, look, my average occupation is going to be equal to minus I times G sigma time-ordered T plus, where T plus means that T plus is the limit of T prime going to T on the upper side, right? Because you want to keep the ordering of your operators appropriate. Now, one way to not be dealing with these tricks is to introduce directly green functions that are connected to operators, to averages immediately. One of them is called the lesser green function, which is I times d dagger sigma t, d sigma t prime, and the other one is the greater green function sigma t prime, which is minus I d sigma t d dagger sigma t prime. So you see that if I take, for example, this green function and I set t equal to t prime and I multiply by minus I immediately have the occupation. I don't have to worry about ordering. So I have plenty of green functions. They are not all independent. Actually, only, for example, out of these 4, only 3 of them are independent, etc., etc. But most importantly, if you are in equilibrium, in thermal equilibrium, what happens is that which? Oh, it's just that I wanted to write it that time-ordered green function, so it stands for time ordering. Right, so so the thing is, if I'm in equilibrium, do I need to compute all of them? No, I don't. Typically, you don't. I'm sure that all of you have some experience, for example, with Matsubara theory, right? So when you do calculations with Matsubara, you do all your mess with imaginary frequencies, Matsubara frequencies, and then at the end of the calculation, you do what is known as the analytic continuation to get retarded or advanced green functions, causal green functions. You never bother to compute these two. But what is the reason behind this? The reason is that when you're when you are in equilibrium, the only thing you want to know about your system is the spectrum. How the spectrum is occupied is dictated by statistical mechanics. Fermi distribution, Bose-Einstein distribution, Gibbs distribution, who cares? But statistical mechanics tells you put that many particles on average there. No, that's the rule. And the implication of this is what I call a bit inappropriately the fluctuation dissipation theorem. It's not really, I mean, it's perhaps a version of the fluctuation dissipation theorem, but it's not the usual fluctuation dissipation theorem we are used to, in which we say, if I want to compute, for example, this green function that is connected to the average of operators, I can easily prove that this is equal to I times A of omega times F of omega, where A of omega is minus twice the imaginary part of the retarded green function, and F of omega is the Fermi-Dirac distribution. Now, this formula is incorporating what I told you before in words. The only thing you need to know is the spectrum, the spectral density. Once you know the spectral density associated to your operators, you know, you don't need to compute how particles are distributed there, and you immediately know the statistical green function, and you know the average of your operators. You know everything about your system. So the only important thing is to know retarded and advanced green functions. And that is why when you do Matsubara calculations, at the end Matsubara formalism works so well. You don't care about imaginary time green functions, right? Yeah, who cares about them? At the end of the day, what you have to do is to make the analytic continuation and compute retarded green functions or advanced green functions. And that is the reason, physical reason. Now, you can write a similar equation for G greater. So this is going to be minus I A of omega F of omega. Sorry, 1 minus F of omega. Right, so now, what is the second problem of non-equilibrium theory, right? So the problem when you go out of equilibrium, that this is not true anymore. You cannot give up on all these many green functions. You have to deal with all of them. And the physical reason behind is that you cannot just compute the spectral density and then the distribution function is given by Fermi and Dirac or Bose and Einstein. You have to compute both the spectral density and the distribution functions, and the two calculations are connected to each other. Okay? So by the kinetic equation. That is the complication.
So these are fluctuation dissipation theorem results. Can I use them if nu well is close to nu r, not very different?
Well, you will see the answer to your question in a second. Okay, so I will ask you to guess the answer to your question in a second. Right? So is it clear? So if you're out of equilibrium in general, you cannot use this fluctuation dissipation theorem. Yes.
So we have those quantities like N, P, I alpha,
Yeah.
AC, and those are connected to this.
Yeah. So for example, N is equal to minus I sum over sigma G lesser sigma T. You see, and if I now use the fluctuation dissipation theorem there, I know that this is equal to minus I sum over sigma integral d omega over 2 pi G lesser sigma of omega, which is equal to minus I sum over sigma integral d omega over 2 pi. So the I A omega F of omega. And then the I goes with the I, and that's what I have. I should put a sigma here. So you see, if I use the fluctuation dissipation theorem, if I want to compute this number, I just compute the retarded green function, take the imaginary part, I have the spectral density, and then compute this integral. The spectral density is essentially telling me what is the weighted spectrum associated to that local operator. right? The one that is explored by creating and annihilating particles with that operator. So I compute the spectral density, multiply it by the Fermi function, and I have the number, right? So is the equivalent, spectral density is the equivalent of the local density of states in classical physics, in a sense, right? So, well, even in quantum physics, right? So, yeah, so all of this doesn't work anymore. You're done. I mean, there's no, you cannot use these two things. In equilibrium, it's just enough one green function. That's why Matsubara works. Because in equilibrium, you can just do your perturbation theory in imaginary time, introduce Matsubara frequencies, do analytic continuation, get retarded green functions. You're done. That's it. Matsubara. Mahan, chapter 3. I'll give you the PDF. You can find it. Mahan, chapter 3. Anyway, so it's a very simple formalism. Instead of doing perturbation theory at 0 temperature, you're doing at finite temperature to compute averages, and you introduce interaction representation in imaginary time. And since you're dealing with imaginary time, your frequencies become imaginary. You will see how it works. But the bottom line of all this story that you don't need to know, because if you know Keldysh, you can do calculations even without knowing Matsubara. The bottom line is that that formalism is just something that is made to compute one green function, G retarded. And once you know that, you know everything because of that. Out of equilibrium, just take it and put it in your closet, okay? It doesn't work. So it's not useful. Right, so we discovered therefore two problems. Yes? Where?
You perform the Fourier transform.
Here?
Yes.
No, because I took it at equal times. So if I take it at different, so if I take it
in the next line,
here,
exponential I omega t.
here,
No, the second one.
here. No, I don't, because it's equal times.
Because it depends on t, but the second line does not depend on t.
Yeah, but it's
So
because.
I assume
Right, so what I'm assuming, okay, I'm making an assumption. You're right, I'm making the assumption that this green function depends only on the time differences. Therefore, I take the Fourier transform. If this was tt prime, I had e to the minus I omega t minus t prime. And I'm taking t equal to t prime, and therefore this is gone. Okay? So I made 10 passages in one. Okay? But I hope it's. I apologize if I'm, stop me if I'm doing too many things. The problem is that you tend to acquire the problems of those who taught you, right, when you were a student. And my professors jumped tons of passages, right? So eventually I had to feel. So, but if you see that you're not following, just tell me, and I will tell the whole story in small steps. All right, so these two things are important. Now we have 10 minutes. So in 10 minutes, we can do the following thing. Well, first of all, I can briefly sketch a calculation that we will need next time. Or perhaps I don't even need to do it. I can just give it as an exercise. Let's put it this way. So next time, we're going to use as the simplest possible problem ever to introduce the Keldysh formalism. And the simplest possible problem is just the same problem that I wrote, in which I strip the problem of all complications, so no spin indices, just one resonant level, and some tunneling. And I'm going to ask myself the simple question. I have the two leads with different chemical potentials, mu left and mu right. And then I will want to know if I connect them with this V. At some time, it's not important when, and I go to the stationary state. What is the occupation of this level? So I just want to compute the same quantity that I have here. How is this level occupied? Right? That's what I want to know. And I will build a very complicated formalism to shoot at a mouse, but that's essentially the goal. Right, but before doing this, let me ask you a simple question. If I just take the equilibrium problem, actually it doesn't really matter. Being a non-interacting problem, spectral densities, the spectrum is not dependent on the occupation because it's non-interacting. Nevertheless, imagine that I have this and I want to compute the green function GTT prime of the resonant level. And in particular, what I want to know is the spectral density, so minus twice the imaginary part of the Fourier transform of this. So can anyone guess what is the spectral density going to look like? It's a function that has a name, so I'm not asking a... Have you ever heard of a Bright-Wigner decay? Now, my professor, my advisor, one of the two, used to tell me that in order to do physics, I have to know two things: Bright-Wigner decay and Rabi oscillations, and nothing else. And he's not right, but it's close to right. Anyway, Bright-Wigner decay is when you have a particle that decays in a continuum. And you see that here is essentially the same physics, right? So I can put a particle here. It's not going to stay here forever. It's going to decay in the continuum. And if I look at how it decays, well, how is it going to decay? It's going to decay exponentially into the continuum. You know that. It's going to decay exponentially with a rate that is given by something like a Fermi-Golden rule, correct? So it's going to be 2 pi density of states times some matrix element squared. What is the matrix element we have here? Well, the tunneling matrix element. So it's going to be V alpha squared, and then I will have to sum over alpha. Okay? So this is going to be the decay rate. Now, it's going to decay exponentially. What is a green function? So I'm going to do the derivation with mumbo jumbo, and then you do the calculation at home, okay? It's easy. You just do equations of motion. Or you read it in Mahan. That's the solution to all problems. So you want to compute this green function. So what is a green function? A green function is the amplitude for the process in which I'm creating a particle at time t prime here, and then I'm destroying it at time t. And when I compute this green function, the green function of this one, you see, I'm creating this guy at time t prime, and I'm destroying it at time t. And I'm looking at the amplitude for this to survive in this, to find it again, to still find it in the resonant level, because it could have gone somewhere else, right? It could have gone in the leads. And here I'm just trying to find what is the weight of the wave function that remains in the resonant level. So not surprisingly, the result is going to be minus I theta of t minus t prime, right? Yeah. Yeah, you're right, but the anti-commutator is, you know, this guy is telling you who comes first. So who is destroyed and who is created, right? So because it gives a certain order to, I mean, okay. So anyway, the result that I'm writing is correct. You can do the calculation. I'll tell you how to do the calculation in a second. I just don't have much time, so I want to get to the end of the lecture where I wanted to get. So e to the minus I epsilon naught t minus t prime. And then, of course, there is going to be the exponential decay because, you know, if I put a particle here at time t prime, it's going to decay out exponentially because of Breit-Wigner. So it's going to be e to the minus gamma t minus t prime. Okay? So that's the Green function that you will get. If now you take the Fourier transform of this Green function and take minus twice the imaginary part, what you get is that A of omega is equal to 2 gamma divided by omega minus epsilon naught squared plus gamma squared. This is called the Lorentzian. So in a sense, your level, epsilon naught, when it's coupled to a continuum and you look at its spectral density, is broadened into a Lorentzian of with gamma, right? So that's what is physically implied by what I'm writing here. And how can you get these results? Well, for example, one thing you can do, and I invite you to do it, is write the equations of motion for this Green function. So write I dt g retarded t t prime. And then use the fact that this I dt, well, here you will get a delta function and then an anti-commutator that will give you 1. And then it's going to act on this. And then you can use the Heisenberg equations of motion to compute the time evolution of this using the Hamiltonian. And you will get the first equation that I have written here. So you'll get that this is equal to theta t minus t prime plus epsilon naught g retarded t minus t prime plus sum over k and I vi of minus I theta of t minus t prime, and then you will have an anti-commutator of ck alpha t d dagger t prime. So that's the first equation that you will get. Then you see that I have another Green function here. So this equation is not a closed equation. So I call this Green function here gk alpha, and I write an equation of motion for this. And it turns out that because of the fact that this problem is non-interacting, I can close these two equations. If it was interacting, I could not. And then you start writing equations of motion forever. And it's not a very good way to solve problems. But if it's non-interacting, then the second equation will look like this. Right? G retard, everything is retarded. Retarded. Well, retarded. And you see that now these two equations are closed. I can solve them. I can solve for G retarded. Now, if I assume that the problem is time translational invariant, then I can solve these two equations by taking a Fourier transform that makes of these two equations just a set of algebraic equations, and then I solve for G retarded. And what I get is that G retarded of omega comes out to be 1 over omega minus epsilon naught minus sum over k and alpha of vk alpha squared divided by omega minus epsilon k plus I 0 plus. So the 0 plus is that small imaginary part that you have to put there in the non-interacting retarded green functions. Right, so now you take this. Imagine that you take these v's to be all the same, and you put a peaked fence spectrum for epsilon k, just a spectrum of all levels with equal level spacing. And now you plot this, right? You take the minus twice the imaginary part of this and you plot it. And what you will get is this. So it's epsilon naught. You will get a bunch of peaks. Like this. And this bunch of peaks, as you send the level spacing to 0, keeping that stuff finite, right, the small imaginary part finite, will become denser and denser, and eventually you will notice that the envelope of these peaks is the Lorentzian I was talking about of width gamma. Right? So that's how the story develops. So typically when we do calculations, we don't think about all this finite size story. The discrete spectrum, we just go straight to the thermodynamic limit and write the Lorentzian. Good. So now that we know that the spectral density is a Lorentzian, let me ask you a question, and then we finish for today, and tomorrow we will have a hard lecture. So the question is the following. I told you that the number is going to be equal to the integral d omega over 2 pi a of omega, f of omega. That is true in equilibrium, right? The Lorentzian, the spectral density of this resonant level for this non-interacting problem is always the same, in equilibrium, out of equilibrium. The spectrum doesn't see the fact that you're out of equilibrium because it's non-interacting. So this is always a Lorentzian. When you're out of equilibrium, what changes is this, is the distribution, is the way you're putting particles inside this continuum of levels, inside the spectral density. So my question is the following. Imagine that I have this resonant level that is coupled to two leads with two different chemical potentials, left and right, with gamma left and gamma right, such that the gamma that appears here in the spectral density is equal to gamma left plus gamma right. Okay? Could you please guess, no calculations allowed, just intuition. Could you please guess what is F non-equilibrium? You just have to guess it. So let me give you two informations in order to guess it better, right? Make the problem easier. If this, imagine that gamma right is equal to 0. What is the distribution? It's coupled only to the left. It's going to be F left with the chemical potential left. So let's call it F left. F left is the Fermi distribution with the left chemical potential. If gamma left is equal to 0 and it's coupled only to the right, the distribution is going to be F right, because you equilibrate only with the right lead. What is sitting in between? It's allowed to make mistakes, even for professors. You're all allowed to make mistakes. I know the answer, so for me it's easy. Yeah, absolutely. You're right. Perfect. So he said F non-equilibrium should be gamma left, F left, plus gamma right, F right, divided by gamma left plus gamma right. That's what it should be. Weighted average of the two guys. Now, the reason I make you guess this distribution is that the next time we are going through a very painful mess of a lot of operators and operations and analytic continuation with the Keldysh contour and forth and back, and then learn how to it's going to be a disaster, a formal disaster. I mean, it's going to be hard to follow, I promised. So you'll have to go slowly. But at the end of the day, the goal of the whole operation is going to be getting this simple result that we will get that you can guess. So you see, all the physical content of all this complicated stuff is just getting simple things that you can all expect from simple reasoning and simple physics. So in a sense, well, it's a pity that physics is forcing us to go in that direction. But I hope I convinced you that if you're out of equilibrium, there's no choice. I mean, the only choice you have is with which green functions you want to work. But you have to work with more than one green function. The only choice you have is which form you want to give your contour. But your contour has to go from -infinity forward and backward. That's life. So the construction is constrained. There's nothing else you can do. It's not something that we can play with. So next time we're going to build it and then eventually get to the application, and you will see that everything is meaningful.
I have a question, like when you said that A omega form will be same, that is only true for non-interacting.
Yeah, only for non-interacting systems. For interacting system, the problem of computing spectrum and distribution are two interconnected problems. For non-interacting system, you can compute the spectrum, and then you have the problem of the kinetic equation, which are separated.
When you say interaction,
Yeah?
when you say interaction,
Yeah.
interacting system you're talking about.
Yeah.
So what do you actually mean by the interaction?
Anything that has four fermion, either two fermion operator, one boson, four fermion operator, anything that is non-quadratic.
So if there are no more questions, let's thank the speaker.
Thank you.